Okay, so I wanted to start with just a clarification about the time-dependent perturbation theory for semi-classical mechanics. This is for Jonatas's sake because he asked this question at the end of class, but he's not here yet, so you can explain it to him later. So basically, yeah, when we were looking at this semi-classical mechanics, basically we're taking a time-dependent perturbation due to the perturbation due to the collision, right, V of t, and we're using that to basically solve for the coefficients of the different zero-order wave functions. So basically we take a expansion of the wave function as some linear combination of zero-order states with coefficients a sub k, and we're plugging that into the time-dependent Schrodinger equation. So IH bar ddt of the wave function equals the Hamiltonian times the wave function, right? So when we take the time derivative, we apply the product rule. We get two factors: one involving the time derivative of the coefficient, one involving the time derivative of this exponential. And then on the left-hand side, we get two terms, one for h naught. The basis states are eigenstates of h naught, so h naught acts on psi k to make energy times psi k. And then we get a second term for the perturbing Hamiltonian, which we don't know exactly what that looks like. But two of these terms cancel, right? So we get left with this. And then this equation, we want to project it onto some final state. So we take a final state, complex conjugate, multiply both sides of the equation by that, and then integrate dr to take the projection onto that final state. This one is just the overlap integral between two basis functions. Assuming the basis functions are orthonormalized, this is 0 unless k is equal to f. And so basically, you only get one term in this expansion that gives a non-zero coefficient here. And that's where k equals f, so you get dAf dt, and you get the energy of the final state here. And then on the right-hand side of this equation, this integral, we don't know what it is, but we're going to give it a name. This is the matrix element of the perturbing part of the Hamiltonian, v of t. So we're going to just take this integral and call it vfk. And it's going to be time dependent, right? Because you're perturbing part of the Hamiltonian is time dependent. And so this is the general solution. You can look back in your notes last time. Whoops. Look back in your notes last time. I made a mistake here. That's why I'm putting this up on the board, just to clarify. I left off the a sub k coefficient here, so you can correct that equation in your notes. Okay, but then the next step, basically I was getting ahead of myself, because in the next step we apply basically the assumption of first order time-dependent perturbation theory, which says that, okay, we assume that we start in some initial state I. That means that initially there's only one coefficient that's non-zero, right? The a sub I coefficient, right, is the only one that's non-zero. And then we're calculating the probability of ending up in some final state f. And so the approximation that we're going to make is that in this expansion, the only coefficient, the only term that's going to matter is the one corresponding to the initial state, right? Because initially a sub I equals 1, all the other a's are 0. And essentially that's the same thing as assuming that there's a direct transition from the initial state to the final state, that you don't have to consider other states as intermediates. You don't have to consider mechanisms where the initial state goes to some intermediate state, and then that intermediate state goes to a final state. So for that kind of mechanism, you need a higher order perturbation theory. But for first order perturbation theory, basically you just replace this summation with just one term where k equals I, and then this is the final result that you get here. Okay, and you can note also that basically if you take an EI minus EF over H bar, energy over h bar has units of frequency, and so you can just replace EI minus EF over h bar with an omega, where omega is the frequency of the transition between the initial state I and the final state F. Okay, so this is the final equation that we're going to use for the semi-classical mechanics. Okay, this is how we calculate the probability of making a transition between an initial state I and a final state F. Okay, so the topic for today then is going to be basically applying classical and semi-classical mechanics to looking at molecular energy transfer during collisions. And so you can consider different degrees of freedom that could get excited during a collision. So here's sort of a table showing typical values of how many collisions are required in order to excite different degrees of freedom from some other degree of freedom. So if you look at translation to translation, this requires only one collision. So it's very easy to transfer basically kinetic energy from one colliding partner to another during a collision, right? It happens every single time. Or, rotation to rotation is also very facile. But typically, for small molecules, if you want to excite rotation from translational energy, that would require something like 100 collisions. And if you want to use translational energy to excite a vibration, that's going to require something like 1,000,000 collisions typically. Okay? These numbers could be a little bit smaller if you're thinking about larger molecules. These numbers are sort of the numbers that you would get if you're considering relatively small molecules, maybe 2 to 5 atoms or something like that. Okay? All right, so the first thing that we're going to consider is translational energy transfer. And so like I said, it's very easy to excite translational energy or transfer translational energy from one atom or molecule to another during a collision. And so if you look at some experimental data, plotted here are speed distributions of a excited sulfur atom that was generated by photolysis, right? So you do photolysis of some molecule, you make sulfur atoms that are going really fast, and they're in a cell that's full of an argon bath gas. So the excited atoms are colliding with the argon atoms, and that basically slows them down. It equilibrates them to the Maxwell-Boltzmann temperature. And so plotted here are the speed distributions after n collisions. So initially, before you have any collisions, this is what the speed distribution looks like of the excited sulfur atoms. After one collision, you can see there's already a significant change in the speed distribution. It shifts to much lower velocities. But then it takes, maybe 5 or 10 collisions before the speed distribution sort of relaxes to that of a Maxwell-Boltzmann distribution at 300 Kelvin, which is shown as markers. Okay? All right. So to consider molecular energy transfer of translational energy, we're going to use classical mechanics. So if we consider, so the topic is molecular energy transfer. And first we're considering translational energy. Okay, so the simplest case that we're going to consider is an elastic collision, meaning there are no internal degrees of freedom that get excited during the collision. And the simplest type of collision that we can consider would be a hard sphere collision. So if you look at the case of a hard sphere collision, then Basically you have two colliding partners. I'll draw them like that. There's a relative velocity vector, right, that's going to cause the partners to collide, or it's going to cause this guy to collide with this one at some point. If we draw a parallel vector to the relative velocity vector along the line of center of the second collision partner, then this distance here is the impact parameter b. Okay? And if you have a hard sphere collision, you end up getting scattering always at the specular angle, meaning if you treat this like a flat surface, then basically you're going to scatter at an angle that is symmetric about the normal of that surface. So basically if you draw sort of a line from the center of the sphere to the point at which the collision takes place, then this angle, this incident angle, we'll call it alpha. Oops. And the scattering at the specular angle is going to be at an angle that's also equal to alpha relative to this normal direction here. Okay, does that make sense? So the scattering angle, if you consider this angle here, chi, that we were talking about before, right, chi is just going to equal 180 degrees, right, so pi minus 2 alpha for specular scattering. Okay? And so, what is this angle alpha? Well, we can write that in terms of the impact parameter. So, if you sort of draw a, if you draw another picture showing, what do these spheres look like at the moment when they collide, right? You have I'll again draw this dotted line connecting the center of the two spheres, right? And so the impact parameter was here, this is b, and then this angle here is alpha, and this distance between the center of mass of the two spheres, this is a parameter that we've defined before. This one's called b max. This is the maximum impact parameter that you could have that would still give you a hard sphere collision. And b max is just equal to the sum of the radii of the particles, r1 plus r2. Okay? And so then, using trigonometry, you can say what alpha is. So the sine of alpha is going to equal the height of the leg over here, which is just b divided by the hypotenuse b max. Right, so sine alpha is just b over b max. Okay, so using this expression then and solving this for alpha, you would have that the scattering angle chi is equal to pi minus 2 times the arc sine of b over b max. Okay? So if you're given b and you're told that it's a hard sphere, so if you know b and you know the radii and you know it's a hard sphere collision, then you can calculate the angle. And then from conservation of momentum, you have that m1 times the initial velocity of particle 1 plus m2 times v2, that's going to equal m1 times the final velocity of particle 1 plus m2 times the final velocity of particle 2. Okay? And so if you know the angle at which particle 1 scatters, and you know the initial mass, or you know the masses, and you know the initial velocities, right, then you have two unknowns. One unknown is constrained by the angle, the other unknown is constrained by conservation of momentum, so you can solve this using geometry to figure out the final velocity of particle 1 and 2, just from conservation of momentum and from the specular scattering condition. Okay? And so if you have a hard sphere, then the scattering cross-section is independent of energy. So the hard sphere collision cross-section is independent of the collision energy. Okay. And in general, the hard sphere cross-section, right, as we've discussed before, this is just pi times B max squared. Okay? But if you want to go to a real collision system, between actual atoms that are not actually hard spheres, then of course this condition doesn't quite hold, and the cross-section is actually a function of energy. So the cross-section sigma equals sigma of the relative energy. Okay, and it's possible to show that if you have a elastic collision, with an arbitrary potential V of R, right? So this would be appropriate for cases where the potential energy only depends on the distance, right? So for scattering of atoms, basically, where you don't have a molecular orientation dependence. Then the scattering angle, you can show that's equal to pi minus, and then instead of this alpha, instead of 2 alpha, you get an integral. You have to take 2b times the integral from Rm to infinity, where Rm is the distance of closest approach between the two atoms. You're going to integrate dr over r squared times 1 minus the potential over the relative energy minus b squared over r squared. Okay, and sorry, so this is to the 1/2. Okay, this expression, it's not so difficult to derive. You can derive this using conservation of momentum and conservation of energy, and then you arrive at this expression, basically. And if you're interested, I can show you which book to look at, for the derivation. But I don't want to do that much classical mechanics on the board for the sake of time. So I'm not going to give you a derivation of this, but yeah, so in this equation, ER is the relative energy. It's 1/2 times the reduced mass times the relative velocity squared. and Rm is the distance of closest approach. So it's the closest distance that the two colliding partners arrive at during the scattering event. Okay, and in general, this is going to depend on the energy, and it's also going to depend on the impact parameter. Okay, and one potential that's commonly used for atomic scattering is the Lennard-Jones potential. So the Lennard-Jones potential, also called the 612 potential. That has the form V of R equals 4 epsilon times sigma over R to the 12 minus sigma over R to the 6. So you can see why this is called the 612 potential. Okay, and let me just sketch what that looks like. So this potential has a, if you plot V of R versus R, this potential has an attractive part and a repulsive part. As R goes to infinity, this is going to go to 0. So this here is 0. The minimum of the well is going to be at minus epsilon. And the point where this crosses 0, that's going to be at R equals sigma. Right? You can see that if you plug in R equals sigma, then these two terms here are going to cancel and you're going to get 0. Okay? So what if you come in, if you scatter with a certain amount of energy, then the classical turning point, if you come in with relative energy epsilon sub R, then you're going to have some classical turning point, right? So this would be Rm. And you can see that if you increase the initial scattering energy, Rm is going to decrease, right? You're going to scatter at shorter and shorter distances. And so since Rm decreases with increasing energy, relative energy, you would expect that the cross-section also decreases with increasing collision energy. And for atom-atom scattering, this is indeed what is typically seen. Okay? Any questions? Okay, so the next topic that we're going to consider is going to be vibrational energy transfer. Okay, so we're going to consider the simple case where we have an atom colliding with a diatomic molecule and it excites some vibration of the diatomic molecule. Okay, and just to make it a really simple model so that we can understand the basic ideas, we're going to consider just a linear geometry where we have some atom A, and it's in a linear geometry with some molecule BC. Okay, and so the distance between A and B, we're going to call that RAB. The equilibrium distance between B and C, we're going to call that little r equilibrium. But if you have a displacement of BC from the equilibrium bond length, right, so maybe you have a displacement where C is over here, then we're going to call that displacement little r. Right, so the instantaneous bond length is R equilibrium plus R. Okay? And so then we're going to want to write this in terms of the distance of the A atom from the center of mass of BC. So the center of mass distance, so the center of mass of the BC molecule, let's say it's here. This distance here from B is going to be gamma times the bond length, where gamma equals the mass of atom C over the total mass of the molecule. Right, so if atom C is very massive compared to atom B, then the center of mass is going to lie close to atom C. If atom B is much heavier than atom C, then this gamma is going to be 0, basically, so the center of mass is going to be close to B. If B and C have exactly the same mass, then gamma equals 1/2, and so the center of mass is halfway between. Okay, so does that make sense? And so then the distance between the A molecule and the center of mass, we can call that R, and that's simply equal to RAB plus gamma times R equilibrium plus R. Okay? So just for clarity, I'll give some definitions. So R is the distance of A from the center of mass of the BC molecule. And gamma, I've already given the definition here. Okay? So usually vibrational energy transfer in these collisions, usually it depends more on the repulsive part of the interaction than on the attractive part. Of course, the attractive part can play a role, but if we just want to model this using a very simple model, we can use a potential of interaction that only includes repulsion between A and B, right? So we're not going to use a Leonard-Jones potential like this, we're just going to use a potential that increases as you get very close. And so a model potential that's frequently used for this type of problem looks like this. We're just going to say V of RAB, so basically when A gets very close to B, there's going to be a repulsion, and we're going to say that that repulsion grows exponentially. So It's proportional to exponent of minus the distance RAB over some parameter rho. And this parameter rho is called the range parameter. And so if you think about this potential, basically when RAB is 0, it's equal to some large number, A, and then as RAB gets larger than 0, basically this exponential is going to decay to 0. And the range of the interaction is described by rho, right? Rho would be the characteristic distance at which the exponential decays to 1 over e of its initial value. Okay? So this is like the characteristic distance for the interaction. Okay? So we're going to take our model potential, and instead of putting it in terms of RAB, we're going to write it in terms of R. So the potential of RAB, right, that's equal to exponential, or A, it's proportional to the exponential of minus RAB over rho. And this is equal to A times exponential of minus, so then substituting this definition, right, solving this for RAB, we're going to get R minus gamma times R equilibrium plus R of the displacement, divide by rho. Right? Okay, and so we can separate this into different factors. So this is going to be equal to A times exponential of gamma times the equilibrium bond length over rho, right? This is just a constant. And then we're going to get times exponential of minus R over rho. So this factor depends on the distance of the A molecule from the BC molecule.